Okay, so what color should we start with? What color? Did somebody say pink? Well, it's just that my class last semester kept asking for pink. So it's giving me a bit of a flashback to last semester. Well, let's have pink, and let's see whether it shows up. I might have to go with darker colors. What should I call this? Rough outline. How does that look? That's fine. Rough outline of the spaces. We're working. Okay, as headings go, it's a bit long. But I just want to give you a very broad brush picture of what this course is about. Could you please keep quiet? We are going to look at moving between spaces. Okay. Now that's what's familiar to you from first year. Okay, going from R to R. Putting in real numbers, getting out real numbers. Putting in X values, getting out Y values. Drawing graphs on a two-dimensional space where your horizontal axis is your input, real number line, and your vertical axis is your output, also a real number line. So you've done quite a lot of moving between R and R. The picture that you would draw to demonstrate a mapping from R to R would be a curve in 2D. Curve. Sorry, my stylus is still on holiday. Okay, so something like this, okay, where this is a real number line, and that's a real number line. And yeah, okay, not much more to say about that. And you've done lots and lots and lots and lots and lots of that throughout school and all through first year maths. So this is your most familiar thing. We are going to widen that into that collection. Yes. Yes, they'll be available on Vula hopefully by the end of second period. Otherwise, it depends on how busy I am. But ideally, I put everything up in second period. Okay. Ideally doesn't always happen, but everything gets made available. The final notes as well as the screen capture video. Right, R2 to R. Okay, so what does that look like? There you're putting in something two-dimensional. So you're putting in a vector. You're putting in X and Y. And what you're getting out is a single real number. What you're getting out is Z. Looks like that. Looks like that. Okay? Input is two-dimensional, output is one-dimensional. The picture that you would draw to demonstrate such a relationship is a surface. There's a paraboloid, rather scruffy paraboloid. There's Z, there's X, there's Y. Your domain is the entire, well, it's either the entire XY plane or it's a subset of the XY plane. But your domain is no longer just about X. Your domain is now X and Y because X and Y are inputs. Okay, so a typical formula, well, let's have a look. Here, a typical formula. One. Here, a typical formula would be Z equals X squared. Okay, that's a paraboloid equation. Soon you will recognize surface equations very easily. Input, two-dimensional, output, one-dimensional. Input, vector, output, real number. Scalar. Okay, and that's surfaces. We're going to deal a lot with surfaces. All right. Then there's the in a real number and getting out a vector. Okay, so you put in a number and you get out a vector. So what does that look like? Input, sorry. I'm going to get backache working at this table. Sure, I'm going to be moaning about this venue the entire semester. You're going to get very tired of it. Input. Input would be t. Okay, we typically use t as our parameter letter, the letter we use to represent our parameter. Another very popular letter to represent parameter is lambda, but basically as long as it's a letter that's not already being used for some other job in your problem. And your output would be xy or xyz. Okay, so the picture that we would draw is something like that. So a typical formula, let's give a typical formula first. Typical formula would look something like T equals cos t sine t. That's a pretty typical one. So your input is just a single number, a value t to the power. And you plug it in, and you have to plug into all three components until the thing you get out is a vector in three components. So I can see this satisfying. Is there something you can do about anything else? Oh, somewhat right, right? Anything getting in between you and understanding the maths? What's yours, please? Okay, so what does that look like? That looks like a space curve. That sort of thing is called a space curve, and in this case, it's a helix. So that's x, and that's y, and that's z. So of course, there's no t. T is in fact it's basically not visible, but t controls. You can think of a particle moving along the curve, and t is the time at which it's at a particular point on the curve. So different values of t would give different points on the curve. It's extremely important. And you've used the idea before in some of the vector geometry. Where you had a line intersecting a plane, and you had to find what was the point where the line intersecting the plane. Now, when you deal with parameters, parametric equations for things are really fabulous, they really are, it's powerful. And every point in space has an x or y z coordinate. There's essentially three unknowns to solve for. But if it's a point on a parametric surface or parametric curve, in fact, there's only one thing you're going to solve for. You shouldn't solve for the parameter that defines that point, because there's just a single parameter that's defined where the point is, and that single parameter will give you your x or y and z. So you do that in vector geometry when you're intersecting lines from a plane. Then you say, okay, I've got a parametric equation for the line, and I've got my plane which has x, y, and z in it. But what I'm going to do is I'm going to replace my x, my y, and my z with parametric expressions from my line equation. Suddenly I've got an equation with just a single unknown in it. And what I'm solving for is the parameter value that defines that point in space. That satisfies the line that remains simultaneously. So we will do that. We will do that exact same thing. Only generally with more complicated curves than lines and more complicated surfaces than planes. So vector geometry in first year was your sort of first dabbling with the stuff that we're going to be doing now. Okay, and then the third thing that we're going to be doing is R2 to R2. Okay, and for that, you still start with tangent vectors, but don't go for it. So what you put in there is vector, and what you get out is vector. Those things are called vector fields. I didn't write the space curve. This is space curve. Curve. And this thing is called a vector field. And what does it look like? A typical formula would look something like f is equal to x squared plus y squared. Please, no talking. Keep quiet, please. So that's a vector field. What you put in is vector x and y, and what you get out is So, a typical thing there is you're putting in a point in space, and what you're getting out is the velocity of the fluid at that point. So, what you're putting in is vector, it's a point in space, and what you're getting out is vector, it's velocity, it's compared to that direction. So, if you want to draw a picture of something like that, you generally draw it as a direction field. Did you do direction fields in first year? You'd have something that looked like you'd have a bunch of points on a grid, and then you'd have like little arrows. That sort of thing. Look familiar? In fact, so those things are applicable to things like fluid flow, fluid dynamics. I had 3 oceanography students sitting on a pitch last week, so that was very applicable to their work. Not just in inside and as well. So that's the obvious application. Where different points in space, different points in your matrix have different vector conditions. Okay, and so we're going to be looking at all of that stuff. We're going to be looking at surfaces, we're going to be looking at space curves, and then space curves and surfaces play very happily together because if you intersect two surfaces, their curve of intersection is a space curve. So that's something that comes up in this course just all the time. Two surfaces intersecting, find the curve of intersection. And we'll also be looking at if you have a curve intersecting a surface with a point of intersection. Yeah, surfaces, space curves, lots of fun. And then vector fields we'll look at slightly later in the course. Okay, so according to my little clock on my tablet, we have 2 minutes left. Why don't you do exercise 1 at the handbook? Just to get your brain back into thinking about some maths. Okay, so question 1. Great.